Okay, so sorry about that, and hope this works better. So what we have here is we have this face. So imagine we cut down the wrapper and we we peeled off the wrapper here. So what would happen with our wrapper? Well, you would have the edge that you cut down. So if I cut right down here, I would have that edge here, right? And then what happens is I would unfold that paper that wrapped around it, and what shape would it make? So imagine this is wrapped around it. To me, this is always interesting because it's kind of like, we think of cylinders as round, and yet the lateral face is a rectangle. It's completely a rectangle here. So I hope you can see that there and think about it. We'll go ahead and start answering some of these questions. So it says, identify the shape of the lateral face. So that shape is the lateral face is the shape of a rectangle. What is the name of the solid formed? Well, this would be a right cylinder. This is a right cylinder. Okay. Now it says determine the volume for the cylinder shown and show your work. Now down here they're going to show you the work, right? And here they're talking about, this is a really interesting concept here. In fact, let me take that tool off and use this tool here, this tool right here. Okay, so it says here to derive the formula of the volume of a cylinder, you can think of the cylinder as an infinite stack of discs. Each disc has an area of pi r squared, right? So like this base down here has the area of pi r squared. And then what we do is we just keep adding discs on top, and we stack. So, really we're saying, oh, this is formed by translation, right? And that's true, it is formed by translation, but one way to think about it is just an infinite stack of these discs. And so then when they get, what we would do is we'd add the area here and add the area and add the area, and we'd keep adding so many times until we times it by h. That's how many times we'd add, right? So it'd be pi r squared times h. There's your volume, right? This is your volume. We'll get into Cavaliere in a minute, but this is basically Cavaliere's principle here. This idea that if we measure the area of every cross section of a three-dimensional solid, and we add all those together, we can multiply it by the height, that will give us the volume, right? So that's one of the things. It says, can you choose any disk in a cylinder and multiply the area by the height to calculate the volume of the cylinder? So yeah, as long as, so thinking about these disks, they've been stacked, right? They've been stacked. So as long as every disk is congruent to the last, then yeah, the area doesn't matter. We can use this area, that area, or any other disk that we should pick, right? Let's put that in there. So as long as the disks are congruent, they will have the same area. So you can use any of the disks to calculate the volume. Top, bottom, middle, whatever. Okay? All right. So it says a two-dimensional representation of a cylinder can be obtained by translating an oval in 2 dimensions and connecting the tops and bottoms of the oval. Now it says translate the oval in a diagonal direction to create a second oval. Well, let's see if I can do that. Here we go. I'm going to try to draw. Oh, I think I have an oval tool here, right? There's an oval tool. Let's see if I can make an oval. That's not really going to be diagonal though, right? So let's try, I'm going to try up here and see if I can get an oval that's a little more diagonal, right? So now, if I connect those, my line tool here, so now we have translated it diagonally. So in other words, what we're saying is this line here to this circle does not make a 90-degree angle, okay? This one would be less than 90, that would be greater than 90, right? So what do you notice about the relationship among the line segments? Well, the line segments are still parallel. We'll put that down there. So the line segments are still parallel. All right. Okay. When you translate a disk through space in direction is perpendicular to the plane containing the disk, the solid is a right cylinder. Otherwise, it is an oblique cylinder. So now Jessica says the lateral face of an oblique cylinder is a parallelogram. Ariana says it is neither a rectangle nor a parallelogram. Who is correct? Explain your reasoning. So maybe it's best to, let's create one again. Let's go back here and make our oval. And then we'll do our very best to imagine this. Okay, so here's our oval, which represents a cylinder. And then here's another, or it represents a disk rather. So, and we're going to say it's a circular disk. And then we're going to connect those with a line. Now this is a three-dimensional object, right? Like a cylinder, but it doesn't, if you look at it like a toilet paper roll or something, but it's not going straight across as a toilet paper roll, right? It's not going straight across. So that's important to kind of notice. So what's going to happen if I cut this? Well, if I were to cut this, let me get a line to cut this with. So, oh man, I wish I had a dotted line. There's no dotted line, is there? No. All right, so we're just going to have to cut it right here. So the key is if I cut this, how would I cut it? Cut it straight across? And what do I end up with? Well, so can you see that? We've got it cut straight across down here. So what's this measure of this angle going to be? What's the measure of that angle going to be? What about this distance and that distance, right? We know the distances are the same, right? Because this cylinder and that cylinder, or this oval and that oval, they're both congruent, right? So we know that the distance is going to be the same. The problem is it's not coming straight down, is it? It's really coming down on a diagonal, right? So it's really doing something like this, and then it's going straight across, right? And whatever that distance is, this distance up here is equal. So what is that shape that we end up with? Okay, I'll let you figure that out. Think about that. Okay, I think you can know that. Oh boy. I've got to take this tool off before I scroll. All right, so now we get to Cavaliere's principle. So, this is really good. This is just a two-dimensional object here, right? So we should be able to measure the area of a two-dimensional object. If you think of a rectangle, you just go length times the width. So here they have the length times the width, but they're calling it a height, right? So length times the height, right? But this has got all kinds of curves and stuff in it, so it's hard to really, it's what we call an irregular shape. So the distance here, but this is the key for Cavaliere, this was the key. All right, the distance across any part of the figure is the same. So this measure here, which they've got it marked L, that length, is L here, L there, and any line I were to draw would also be L. All right, wherever I draw it, that's also all these lines, every single one of them measures L. So now, this is what Cavaliere said. He said, let's approximate the area by making it into rectangles. So you have these rectangles. Now notice that each rectangle is off a little bit, right? It's not quite a rectangle. There's a little extra here, there's a little less there, right? So what would we do to find the area of this two-dimensional object? Well, we would measure the area of each rectangle. Let me type that out here. Ready? And you write the same in your book. Here we go. So we would find the area of each rectangle. Then we would add all the rectangles together. Okay? So what is the approximate area of the regular shaped figure? Well, it would be, the length times that height of the rectangle, right? Or the irregular shaped figure. So I would have this rectangle plus this one plus this one plus this one. How many times? H times. So length times height. Okay? So if this irregularly shaped figure were divided into 1,000 congruent rectangles, what would be the area of each congruent rectangle? So here we have it, it's divided into 10. 10 congruent rectangles. So each of these, actually, we should probably even do better with this formula. Let's go back and look at this formula again. Okay, so we can really get it. So they're asking us, what is the approximate area? Well, it is, L. It is actually 10 times the length times the width. Whenever we find the area of one, right, rectangle, and then we would multiply by 10. So I'm going to write that out. We would find the area of a rectangle, length times, what the heck? Hit the wrong button there, times width. Then multiply by 10 because we have 10 congruent rectangles, right? So then the next thing they're asking us, what about if there were 1,000? Well, we would still find the area of each rectangle, length times length times width, then multiply by 1,000 because there would be 1,000 rectangles, right? So what if it was divided into n congruent rectangles? So we would still have the area of each. So the area of each rectangle times n, right? So we'd have n rectangles. So what if it was only one rectangle? What would be the approximate area of the figure? So the approximate area would be length times height. It says compare the area of the two figures shown. Each figure has a height of h and a base of length. So if I were in class with you, I think what I'd really try to do is just maybe show you, like if I stacked a bunch of books, right, and we'd covered them up with a paper, or if we had some strips, would it really make much difference if I shifted those strips of paper off to the side? Would that really change these areas? If every single area, every single rectangle was congruent to the last, would it matter at all that we shifted them? Okay, this is Cavaliere's principle for two-dimensional figures, sometimes called the method of indivisibles. If the lengths of one-dimensional slices, so if each of these slices, and they're one-dimensional, so now we're just talking about lines, they're just segments, right? They're just a line segment. If all the lengths of those lines, each slice that we made, were the same, then all we'd have to do is, the two figures would have the same area. We would just take all those slices, add them up. Who cares if it got pushed to the left or the right? It's going to be the same whether we stack them in a right formation like a rectangle or if we got in some irregular formation here. Okay? We take, it says this is best illustrated by making several slices of one figure, like a sheet of paper, but then when we just slide them one side to the other, it looks like a different figure, but the area really hasn't changed. So now we're going to do the same thing with prisms. Here we go. Here we have a right rectangular prism and the oblique rectangular prism. So what geometric figure represents a cross section of each rectangular prism that is parallel to the base? So now we're going to cut across in a way that's parallel to the base. So let me just imagine that here, right? And I'm going to get a brighter color for this. Okay, so I'm parallel to the base means when I cut across, it's going to come across parallel to that base, right? Okay, well then I'm going to end up cutting back there. So what's that shape going to be? So the answer is that each slice is still going to be a rectangle. It's going to match the base, right? Each cross section matches the base. So let's write that down. So each cross section would match the base. So if the base was a rectangle, then the cross sections would each be rectangles too. What are the dimensions of one cross section? Well, that's length times width. So that is length times width. Okay, and what is the volume then? So if one slice is length times width, and then we had, just like Cavaliere said, each slice was congruent. Who knows how many slices there are, right? But there's so many of them. They're stacked h high. Does it matter in this three-dimensional object if each slice was stacked straight up or to the side, like this oblique? Does it matter if it's right or oblique? Well, not if the areas are the same and the height is the same, right? So the volumes would be the length times the width times the height. Another way to say that is to say the area of the base times the height. Find the area of that base and just multiply by the height, and that's our volume, right? It says approximate the volume of the oblique rectangular prism by dividing the prism into 10 congruent right prisms as shown. This is what Cavaliere said. Look, let's just slice that prism up into 10 different rectangles, find the area of each one, and then, multiply. And you can do it with 10, you can do it with 1,000, you can do it with n number. It doesn't matter, just like he said with the two-dimensional irregular shape we had a minute ago. Remember that two-dimensional irregular shape. Same thing here. This is a three-dimensional irregular shape. Doesn't matter as long as each slice is congruent, right? You can have thousands of slices here or billions of slices, whatever it is. You would still just find the area of any one of the slices and multiply it by the height. Okay? That's Cavaliere's principle for three-dimensional figures. Given two solids between parallel planes, if every plane's cross-section parallel to the given planes, so top and bottom, the bases, and if every single cross-section had exactly the same area in both solids, the volumes are going to be equal, right? This is really easy to see with like quarters, right? A stack of quarters here, imagine that. And does the volume change because we just tip it to the side? And the answer is no. And so now the volume of the right cylinder and the volume of the oblique cylinder, if they have the same dimensions, they're going to be the same. So how would we calculate it? Well, we would still find the area of the base times the height. In this case, because the area is a circle, the area of the base is a circle, so we would do pi times r squared. I'm going to do this for squared. And then we would multiply that by the height. Okay, so pi r squared for a circle times the height. Using Cavaliere's principle, what can you conclude about the volumes of these two principles, assuming their heights are equal and their bases are congruent? So if the bases are congruent, right, the heights are equal, what are we going to say? the volumes would be equal. It's important to mention Cavaliere's principles do not compute exact volumes or areas. It's not meant to calculate an exact volume or area. The principles just show that volumes or areas are equal without computing the actual values. Cavaliere used this method to relate the area or volume of one unknown object to one or more objects for which the area or volume could be determined. All right. And just to go back, one other thing I think I'd like to show you here. Remember, we have, this is the area of the base, right? The cylinder. This is the height. But now we have this thing slanted here. And that's where you get this measure, the outside measure of this cylinder, this oblique cylinder, which we would call the slant height. It's not the same as the height of the stack, right? It's not. It's the slant height. It's a little bit different, right? Same thing here. This diagonal here, this edge of this triangular, oblique, triangular prism, that edge does not measure the same as this edge, right? But this edge does measure the same as the height. So even though I'm pushing it to the side, that edge gets longer and longer over here, right? That's why we call this the slant height, and this is called the height. Two different measures, okay? Okay, that is what we're going to do here for covering Cavaliere's principle and volume formulas and our three-dimensional figures, okay? We're going to go ahead and continue on to lesson 4.